Our next speaker is Salma Mohideen from Stanford University.
Hello, my name is Salma, and I'm a third-year undergrad student, and I work in Phil Buxbaum's lab. And first of all, a huge thanks to all the people who helped me with this research and put the slides together. So basically, our study was imaging acetylene dynamics with cross-polarized pulse pairs. And so we did a polarization-dependent study of enhanced strong field ionization in acetylene, and it revealed multi-channel dication dynamics. In our study, we did a pump probe cross-polarized pair of pulses with some varying time delay between them. And one of our main observations was that enhanced ionization occurs in the dication state of acetylene, and we associate this with carbon-carbon bond elongation. Also, we found that the molecule's orientation in the laser field has a dramatic impact on which orbitals become vacant. So, to give an overview of the enhanced ionization concept, it's a phenomena that's pretty well known to occur in a lot of different molecules. Specifically, this paper, Kitzler et al., studies how enhanced ionization occurs in acetylene. And the main ideas are that once you reach the acetylene cation and dication state, it initiates some carbon-hydrogen bond stretching. And when the carbon and hydrogen bonds stretch, it causes these interpotential barriers to arise. And at some specific carbon-hydrogen bond distance, the electron, which is localized at these barriers, can more readily tunnel through. And so you see an enhancement region occurring at specific time delays. And over here on this plot on the right, we see the two main effects which lead to enhanced ionization. The first one is that as the carbon-hydrogen bonds stretch, you should see that the curve monotonically decreases because the repulsive force between the carbons and hydrogens causes less kinetic energy to be released upon Coulomb explosion. However, at the same time, you should see a region of enhancement which correlates to the critical bond distance. Also, there's been a lot of ab initio modeling that demonstrates strong polarization dependence of ionization rates in acetylene. Specifically, this study, Rusafek et al., shows that the polarization of the acetylene has a huge impact on which orbitals will become vacant. Specifically, if the acetylene molecule is aligned with the polarization, then you should see that the red, blue, and green curves have similar ionization rates for our experimental intensity of 10 to the 15 watts per centimeter squared. So this tells us that if the acetylene molecule is aligned with the polarization of the laser pulse, that we should see similar ionization yields out of the pi and sigma orbitals. However, for the same molecule, if it's aligned perpendicular to the polarization, we see that the blue curve has a much higher probability of being ionized. This tells us that if acetylene is perpendicular to the polarization, we are more likely to ionize out of the sigma orbitals. So our study aims to understand the relationship between polarization and also how this can affect enhanced ionization in acetylene. So we use ultrafast techniques to initiate and subsequently probe acetylene's polarization-dependent dynamics. Specifically, we use a pair of cross-polarized pulses with varying time delay. The first pulse will do an initial ionization of acetylene, and this will initiate some molecular dynamics. And after some varying time delay, we further ionize acetylene, and that causes it to dissociate. We use VMI technology to capture the fragments and study the geometry during the dynamics. Specifically, we have an electric field which pushes the positively charged fragments towards our detector plate. And then we get an image similar to this one, which shows the X and Y positions on the detector plate. And using information about its X and Y positions on the detector plate, as well as its time of flight to reach the detector plate, we can recreate a 3D reconstruction of the total momentum of each fragment upon dissociation. So that allows us to come up with curves like this. By understanding the momentum as well as the charge and mass of each of the particles, we can understand the total kinetic energy of each fragment. Summing these kinetic energies, we get the kinetic energy release. And looking at the kinetic energy release versus time plot, we show some clear signs of enhanced ionization. Specifically, we saw a lot of enhanced ionization occurring in our very highly charged states, our highest charge state was the 6 times ionized version of acetylene, which comes from an hydrogen plus, carbon 2 plus, and carbon 2 plus. But in the interest of looking at more data, we can look at the captured fragments of the 2 ion coincidence, carbon 2 plus, carbon 2 plus. And this shows us some clear signs of enhanced ionization. And this becomes even clearer if we look at the 3D version of this carbon 2 plus graph. Here, in this 3D model, we look at kinetic energy versus time delay on the x and y axis, and the z-axis height represents the counts of ionization for those specific quantities. And so we see a specific peak here, which correlates to an enhanced ionization region. And in this region, the molecules are about 3 to 4 times as likely to become ionized. And this occurs when we have a 20 femtosecond delay between the pulses, and there's about 20 EVs of kinetic energy released. So we think that this enhanced ionization region for this highly charged state is possibly caused by carbon-carbon bond elongation. So in order to further test this theory, we made a one-dimensional model of the carbon-carbon dissociating, and it replicates experimental highly charged states. Specifically, we looked at a one-dimensional cutout of the potential energy surface for this state of the molecule, the 3 sigma U state. And we formed this state by removing 1 electron from the 2 sigma U orbital and 1 electron from the 3 sigma G orbital. And so combining this curve with a 1 over R Coulomb dissociative curve, we can get a model of what kinetic energy should be released from this Coulomb explosion. And so here, the lower curve shows the kinetic energy release as we propagate along this potential energy surface that should be released from the carbon-carbon bond elongation, considering that the hydrogens are in place. However, if we repeat this model propagating along the potential energy surface for carbon-carbon bond stretching for just the carbon-carbon bonds, then we can see that both of these curves fit the experimental data, and specifically, we can assume that the hydrogens leave very early. And we see that in this enhanced ionization region, along with our experimental model at this enhanced ionization region for this kinetic energy, the carbons should be about 3 angstroms apart. And so to further understand how polarization impacts the enhanced ionization, we can look at the polarization dependence during 3 main regions. This upper right-hand plot displays the same information. It shows the angular dependence versus time of the molecule. And specifically, we look at the angle between the carbon-carbon bond and the pump pulse. Another way of visualizing this is looking at the one-dimensional kinetic energy release plot and splitting it into 3 main time regions. The first region is at the beginning of the enhancement and somewhat before the enhancement occurs. During the middle section, this tracks the polarization during the enhancement, and at the end, we track the polarization at late time delays. So if we look at the polarization that occurs at the beginning of the enhancement, we see that it's mainly aligned along the probe. However, there's some alignment along the pump pulse. And if we look at the polarization during the enhancement, we see that it's isotropic, meaning it has some alignment along the pump and the probe pulse. And at the end of the enhancement, at very late time delays, we see that the molecule seems to be very much aligned along the pump. And so we can explain this polarization dependence by understanding that there's 2 somewhat competing effects. We see that at late time, the molecule seems to be aligned along the pump and perpendicular to the probe. And this is obvious because we are attributing this state to the carbon-carbon dissociation, and this can only occur when the molecule is aligned along the pump, and so therefore we can remove two sigma orbitals with the initial pump, and that allows for the carbon-carbons to stretch. However, we see that at early time, there's a completely different behavior. And this can be attributed to the fact that enhanced ionization occurs as a result of these interpotential barriers being formed. And so when the molecule is aligned, parallel to the probe pulse, it allows for the the electron to tunnel through any one of these barriers, and that leads to the enhanced ionization effect. So in a summary of what our experiment did, we did a polarization-dependent study of enhanced strong field ionization in acetylene, and it revealed multi-channel dication dynamics. Also, we studied the motion of the acetylene, ionized acetylene, as initiated by cross-polarized pulse pairs, and we varied the time delay between the pulses. And we observed that enhanced ionization can be attributed in the dication state of acetylene to carbon-carbon bond stretching. Also, we understand that the molecule's orientation within the laser field has a dramatic impact on which orbital vacancies are formed. Thank you.